Our homework check asked us to define ln of x the way we did in section 5.1. And it's defined as the area under the hyperbola 1 over x from 1 to x. In other words, this definite integral. Remember, we have to use dummy variables for this function 1 over x because we've used x in the index. And yes, the natural log of x does mean log base e. And yes, that function is the inverse of the exponential function base e. But this was the definition. This definite integral and that area geometrically is the definition of the natural log of x per our reading in section 5.1. Number 2 in the homework check was to find the derivative of this natural log function. You could do 1 over this, so the reciprocal of that, times the derivative of this white stuff. So you have to use the quotient rule, but I wanted you to use the properties of logarithms, that the logarithm of a quotient is the difference of those logs, numerator minus denominator, and that the logarithm of a product, this yellow box times that yellow box, is the sum of those logarithms, and that a power, the natural logarithm of something to a power, is equal to the power times that. And once you get it to this stage, we've taken our single logarithm and rewritten it as 3 separate logarithms. Now we can do the derivative much more easily, obtaining this first derivative. And then I asked you to evaluate this definite integral. We used a u substitution. A lot of you, after you did the antiderivative, you let u equal x squared plus 1, and then evaluated using the fundamental theorem of calculus from 0 to 3. Whereas I left it this way and said if x is 0, then u is 1. And if x is 3, then u is 10, and just evaluated it that way, and we get the same answer. On my B day, we had a quick discussion about the golden ratio because it's related to my birthday and the fact that my birthday next Wednesday will be the 10th Fibonacci number, and the successive ratios, or the ratio of consecutive Fibonacci numbers, approaches the golden ratio the further along you get down that sequence. So we explained that the golden ratio is really just the perfect middle of 2 specific numbers. Now the perfect middle of 2 and 50 you might think is 26 because it's 24 away in both directions. That's the arithmetic mean. But the perfect middle in terms of multiplication would be 10 because it's the same distance in between 2 and 50 by multiplication by 5 and by 5. So that's the geometric mean. In other words, 10 over 2 is equal to 50 over 10. 10's right in the middle of 2 and 50. It's a perfect geometric mean, and this is a proportion, and the Greeks were obsessed with proportions and ratios. So if you want to find the value of the golden ratio, it happens to be not the mean of 2 and 50, but the mean between 1 and 1 bigger than itself. So if phi is the golden ratio, and it's exactly in the middle of 1 and 1 bigger than itself, 1 and 1 bigger than itself, then it's going to have that perfect proportion where the entire segment divided by the big part is equal to the big part divided by the small part. When you solve this equation, we get the golden ratio, 1 plus the square root of 5 divided by 2. Anyway, that was a quick discussion explaining exactly what the golden ratio is. There you have it. So we were keeping track of all the antiderivative formulas that we knew, and we didn't know secant. This doesn't work. A couple people in both classes said, can't we just think of it as 1 over cosine and then do the natural log of cosine? And we've realized really quickly that it doesn't work. If you take the derivative of the natural log of cosine, you get 1 over cosine, but then using the chain rule, multiplied by the derivative of cosine, which does not give us the integrand. So that doesn't work. We had to use, well, this is one way of doing it, this very clever algebraic trick, and we all discussed that. You know how it goes, and there's the formula. Oh, I had a summary of 5.1 and 5.2. We defined the natural log of x. We talked about taking the derivative. We looked at integrals that use logarithms with u substitutions. And then we reviewed all of the integration formulas that were related to trigonometry. There were 10 of them total, the 6 basic trig functions, and then these as well. So here they were. You now know how to do the integral of sine and cosine, tangent and the cotangent, secant and the cosecant. And we know how to do the integral of secant squared and cosecant squared, and of secant tangent and of cosecant cotangent. All right, section 3 is about inverses. You should know all these things. The definition, how the domain and ranges swap, how for any point on one function, if you invert the coordinates, you'll have a point on the inverse, how there's symmetry on inverse relations over the line y equals x, like this exponential function and this log function, and how if a function's definition means that it has to pass the vertical line test, so the red is a function because any vertical line anywhere only hits 1 point, same for the blue, then the inverse relation, if we're just swapping the x's and y's, means that for any given function like this red one, its inverse relation is a function only if this one passes the horizontal line test. All right, and here's a quick example that practices all of this stuff. We did this one in class. Let's find the inverse function of f if f is 3 sine of x plus pi. So this gray function is sine, but this vertical transformation will make our maxes and mins be 3 and negative 3, and this horizontal translation moves our curve. Here's this point. It's going to move it pi to the left. So our function looks like this, and we're going to restrict the domain to a place that passes the horizontal line test, because this function has an inverse relation that's not a function. So if we restrict it to a domain like from negative pi over 2 to pi over 2, then that part of the function, which is encompassing all of the y values in the range of that function, now this passes the horizontal line test, and the inverse relation will be a function. So we're going to restrict f's domain to x values between negative pi over 2 and pi over 2, and the range between y values of negative 3 and 3. All right, you know how to do this. We swapped. Finding the inverse function means swapping the x and y variables, solving for y, and once you solve for y, change it back to the inverse notation. There we go, and now we have to be specific about its domain and range. Its domain will be from negative 3 to 3, and its range will be from negative pi over 2 to pi over 2. To graph that inverse relation, just take these endpoints, negative pi over 2, 3, swap them, and go 3, negative pi over 2 for that endpoint. And for this endpoint, pi over 2, negative 3, plot negative 3, pi over 2. And then for the curvature, a lot of ways of thinking about this, but if it's flipping over the line y equals x, we've got this curve this way. So on this side, it's going to be curving like that. And there's a nice little graph of the inverse function. For the formula for the derivative of the inverse function, first, this is the notation we use, f inverse inside of parentheses, and then the derivative mark. So if you ever forget this, just write the definition of inverse functions. F of f inverse of x is just x. They undo each other. And then take the derivative with respect to x, giving us 1 on the right. Use the chain rule here, so the yellow f prime of the inside times the derivative of the inside, and then solve for the derivative of the inside. And there's the formula. And you can memorize that or be able to derive it just that quickly. Next, for an example. All right, right here is the example. Find f inverse prime of 3 given this function. So the first thing to do is to write down the formula that should be memorized or derived quickly. Notice in this formula, to answer this question, we need to know what f prime is, and we also need to know what f inverse of 3 is. So those are the two things we need. F prime is real easy. We just take the derivative of this function. So really, the only challenging part is finding f inverse of 3 when we're given this function. Well, my advice to you was to make two columns, one with f of x, and put an ordered pair that's blank and blank, and f inverse of x, or in this case 3, and put a ordered pair that's blank and blank. And keep in mind, we want to know the output when f inverse of 3 is asked for. So that means the input into the inverse function is 3, and we want to know this. We don't know that yet. But we know that if this is 3 for the input, it will be the output in the inverse function, and we can easily find what the input is that gives an output of 3 in our function a quarter x cubed plus x minus 1. So we'll find the x value there, which is 2, and once you found the x value there, that's the y value for the inverse function, and that's what we needed to know. So our answer is 1 over f prime of 2. And f prime of 2 is just 3/4 of 4, which is 3 plus 1, which is 4. Last thing was about e and the function f of x equals e to the x. The definition of e comes from compound interest. It was Jacob Bernoulli, they say, who first came up with this. If you invested a principal of $1, earning 100% interest rate, so r is 1.0, being compounded n times a year for exactly 1 year, you would have 1 times 1 plus 1 over 1 to the 1. You'd have 1 plus 1, which is 2. 2 to the 1. You'd have $2. And if you compounded twice in a year, then that would come out to 2 1/4. And if you did it 10 times, 259. 1,000 times is 272. 1,000,000 times it is 272 with this much accuracy. And Bernoulli proved that if you compounded continuously an infinite number of times per year, that $1 would be worth exactly E dollars. So that's where E comes from. That's its definition. But in the definition in our textbook, or if we think about it geometrically with the hyperbola, if you do the definite integral, the area from 1 to E under the hyperbola 1 over x, that is equal to 1. So to get exactly 1 square unit, you'd stop at E. That's another way of thinking about E. All right, what else? The derivative and integral of e to the x. If f is e to the x, then we know the derivative is itself. Wow, that's the only function we've ever met where the slope of the curve is exactly equal to the y value of the curve. So at 0, 1, the slope there is exactly 1. And at the point 1, e to the 1, the slope there is exactly e to the 1. Well, we've seen this before. Could you prove it if you needed to? Maybe try it on your own right now. Here's a quick proof. And take the derivative of both sides with respect to x, which leaves us with 1. Don't forget the chain rule, 1 over that expression times the derivative of the expression. And it's that simple. F prime of x is just f of x, which was e to the x. And if e is raised to a differentiable function of x, then f prime of that function is again just e to the u, but then you have to use the chain rule times the derivative of u. Then of course the antiderivative is itself plus a constant. And what if the numerator is a differentiable function of x? It's still just this. And this was not expected from my class. My class thought that there needed to be 1 over the derivative of u here, but that's not the case. If we're doing the antiderivative with respect to u, and this is e to the u, it's just going to be e to the u plus c. You might say, how is that possible? If we went backwards and took the derivative of this function, would we get that? And you're thinking the derivative of this is e to the u times u prime. But that's if you're thinking in terms of the derivative with respect to x. This integral is with respect to u. So in this sense, u isn't a function of x, and this works just like it works for here. What that means and doesn't mean is the following. It doesn't mean we can say that the integral of e to the x squared dx is equal to e to the x squared plus c. You might think, isn't that what the formula says? E raised to a function of x is just e to the function of x? That's not what it says. And if you try to go backwards, this doesn't work because the derivative of the c is 0 and the derivative of this is e to the x squared times 2x, which isn't that. So how does this formula make sense in this case? This is a counterexample. It doesn't work that way. The reason it doesn't work that way is the formula says e to the u du equals e to the u plus c. So if u is x squared, is this du? It's not. If u was x squared, then du would be 2x dx. So this formula would say, if you had this, then you basically have e to the u du, and the answer will just be e to the u. So if u is x squared, du is 2x dx, and so what we really have here when we do the substitutions is now e to the u times 2x dx, which is du. So you see the formula does work here. This formula says that this will be equal to e to the u plus c, which is e to the x squared plus c. And for the original problem, if you actually take the derivative of this, we will get e to the x squared times 2x, which is the integrand. So it does work. It does work. A few other things about e. If y was equal to e to the x and we took the natural log of both sides, then x would equal the natural log of y. Now this is really just saying they're inverse functions, right? If you take the log base e of the exponential function base e, they cancel each other out the way square rooting cancels out squaring, the way times 7 cancels out divide by 7. Log base e of exponential function base e cancels each other out. We're left with x. Similarly, exponential function base e raised to the log base e, again, they're inverse functions and they cancel each other out. Really, that's it. I don't have a few other things. That's all.